Hi guys, good to meet you. I think the room is a bit dim. Let me turn up the brightness a little bit. How are you doing? Are you in the happy mode or survival mode? Surviving?
Torture us with the workbooks.
Did I? Well, yeah, the workbook. The workbook is where most of your grades come from, right? 60%. So you should expect to do more work on the workbook. So we really want you to learn many of the things from the workbook and not penalize you for using it as an assessment. So really, it's part of your learning process, and I'm afraid I have to impose quite a lot of questions. But think about like one lecture, 4 or 5 questions is not too bad. The weekend ones are a bit longer. And as we are getting through more of this technical discussion about Boolean algebra and K-maps, these are like new representations and new visualization tools. I sort of have to put down a bit more practices than normal. So today we're going to continue our discussion on Karnaugh maps. So to use Karnaugh map to represent functions, to minimize functions, and to even apply operations through Karnaugh maps. And the goal is really to find the minimum SOP and POS expressions. We tried a few exercises from yesterday, and today we're going to see a systematic method to approach the minimization problem. Essentially an algorithm that always allows you to find the minimum expression by visually examining the Karnaugh map. And then towards the end of the lecture, I want to bring up one important concept, which is the distinction between specification and implementation. Specification is how you describe the behavior, and implementation is how you implement it. They may sound the same, but they really are not. And then we'll see their distinctions once we finish our discussion about Karnaugh maps. So with that, I'll switch my presentation device, and then let's get started. So this is the goal. This is what we're doing. We're trying to get a minimal 2-level circuit. Why we're dealing with 2-level circuit? For one thing, it's a very simple structure. So you can define, the object. You can define a very clear optimization objective. In particular, we want to minimize the number of gates and also minimize the number of gate inputs. In a 2-level circuit, you always have a single gate at the final level. If it's a sum of products, you have an OR gate. If it's a product sum, you have an AND gate. So you always have a single gate at the last level. So what we mean by minimizing the number of gates is really to minimize the number of gates in the first level. Yeah, SOP, that means minimize the number of products. Yeah, POS, that means minimize the number of sums. And secondarily, we want to minimize the number of gate inputs. The gate inputs are essentially, you count the number of gates, lines going into each gate. So there are 2 inputs, 3 inputs, 3 inputs, 3 inputs, and add them together. That is the total number of gate inputs. And the reason why we want to minimize it is because a gate with 2 inputs is cheaper than a gate with 3 inputs. It is cheaper in many senses. It's cheaper in terms of area, in terms of power, and also in terms of latency. And for that reason, we want to essentially build the smallest circuit with as few gates as possible. And with the same number of gates, we want each gate to have the fewest inputs. And then we have learned actually a few tools to do this task. Number one is Boolean algebra. Algebraically, you can manipulate the expression, apply things like absorption, elimination to reduce terms and reduce the number of literals. You can also approach it from the truth table. Even though getting the implementation from truth table, particularly the minimum one, is not usually straightforward. You have to really try many things, right? Identify, like visually examining all the conditions. 3-input function is going to be 8 conditions, and see which one can be grouped together. And now we're seeing Karnaugh map. Karnaugh map is a way to plot minterms and maxterms in this 2x2 or 2x4 or 4x4 table and be able to visually identify adjacent minterms and adjacent maxterms. We order Karnaugh maps in this 0001, 1110 order so that between 2 adjacent rows, or even if you have a 2x4 Karnaugh map between 2 adjacent columns, they only differ by 1 bit in their binary representation. And this allows you to combine adjacent minterms or maxterms into larger products or larger sums. So between truth table and Karnaugh map, you can make an easy conversion based on the indices of minterms and maxterms. So you have a min term at index 3. So M3 translates to 0, 1, 1. You put down a 1 over here. If you see a 0 at, let's say, 0, 1, 0, that is your max term 2. So M2, 0, 1, 0, 0, 1, 0, you put down 0 over here. So you can look at them in terms of the binary representation, 0, 1, 0, 0, 1, 1, or in terms of the decimal indices. Both of them are equivalent. And you can also get to a Karnaugh map by just plotting the minterm maximum expansions. Again, based on either the Boolean expression A prime BC that translates into the cell of 0, 1, 1. So 0, 1, 1, you put down a 1. Or in terms of the indices of the minterms. Right? Same goes for the max terms. We expect you to be able to comfortably make conversion between these representations. From truth table to Karnaugh map, from expansion to Karnaugh map, or also the other way around, from Karnaugh map recovering the minterm expansion by just identifying all the minterms and then finding out the binary representation or the decimal representation for those positions. Or from Karnaugh map to truth table, which essentially is doing a reordering of the zeros and ones within the Karnaugh map. To do two-level minimization, we care a lot about product terms and sum terms, a way to group together adjacent ones and adjacent zeros. So here I'm showing an example where we can plot some product terms in a Karnaugh map by finding out a group of ones. So if you have those group of 4 ones sitting at the right column, they really correspond to the condition of A equals 0. So you can represent it as a single literal A. And this smaller group of 2 minterms, they correspond to the condition of BC equals 1, 1. So you can write it out as a product term of BC. And therefore, when the input values sent into the circuits are 1, 1, this term will produce a 1. And in the sum of product expression, 1 or anything gives you an output of 1. Right. And you can have this is actually exactly the same as Boolean algebra. In Boolean algebra, you can apply uniting multiple times to combine 2 minterms and combine 2 implicants into a larger implicant. And but Karnaugh map gives you a much brighter visualization. You can arrive at this minimal set of product terms by just visually identifying groups of zeros and groups of ones. Right. So this is where we ended our discussion yesterday, to plot some sum terms, max terms and larger sum terms in a Karnaugh map. And when we do max terms, we remember that the way we identify the indices of the max term is a little bit different from that for minterms. For minterm, if you have 0, 1, 1, that's minterm 3, represented as A prime BC. For max term at index 0, 1, 1, it is still max term number 3, but you represent it as the opposite of the the binary value of the 3 input values. So 0, 1, 1 is represented as A plus B prime plus C prime. Right. Same goes for the sum term. The way we write down a sum term, let's say A prime B, is we're going to looking for the rows and columns that correspond to A equals 0 and B equals 0. So the opposite of what they appear to be. So A equals 0, B equals 0 corresponds to the top left corner. A equals 0, these 2 rows, that's B equals 0. So this group of 2 zeros is the sum term of A plus B. And similarly, A plus C happens when A equals 0, C equals 0. So A equals 0 is this column, C equals 0 is the top and bottom row. So these 2 zeros, by wraparound adjacency, they can also be grouped together into A plus C. And again, we expect you to be able to convert in both directions. From here to that Boolean expression, that's essentially logic minimization, right? Like given some definition of minterms and max terms, finding me the minimum product of some expression. Or the other way around. I give you the expression, be able to plot it in the Karnaugh map. And why is plotting important? Maybe I'll give you a non-optimal implementation and ask you to minimize it. You can do minimization using Boolean algebra, or better yet, do minimization through Karnaugh maps. Any questions? Any questions so far? All right. So here's an exercise I want you to try out. Given these 2 functions, could you find the minimal sum of products and product of sums? This is actually the same function, right? I'm just duplicating this table twice. Finding the SOP and POS in the minimal form for this function. I'll give you 2 minutes to work on this exercise. And by the way, there are two things I want you to keep in mind. Number one, never forget the wraparound adjacency. And number two, there may be more than one minimal solution. Right? There could be multiple equivalently minimal expressions. Same number of gates, same number of gate inputs. There are just some alternative solutions. Right? If anyone has some questions during these exercises, just let me know, and then I can come over and help you out. Right. And this is a good chance for us to sort of take a break and then do some practice and then getting some individual help. All right, another 20 seconds. All right, time's up. So I want to hear a little bit from this side of the class. So maybe Ryan, did you find any expression, either SOP or POS? Not yet. What about you, Hamza? For the sum of products? Yeah. So BC. BC or A prime CB. So let's verify this solution. So A prime CB, that happens when A equals 0, B equals 1, C equals 1. So it's this min term. Right? For sum of products, we're looking for ones. Right? We're trying to take the summation of all the ones to construct a function. And that's the singular one. And we just have this group of ones. Right? They have wraparound adjacency. And what are the input conditions they share in common? Well, both of them have B equals 0 and C equals 0. Right? That's the joint condition to cover those two min terms. And that can be represented by actually B prime C prime. So we will use B prime C prime in the expression. Again, we're dealing with min terms. So when you see a 1, that is non-complemented variable. When you see a 0, it gets complemented. Right? What about product of sums? Anyone got the POS expression they want to share with us? Yeah, Judy, what's your POS? B naught plus C. A naught plus C naught. Right. The last one is a B plus C naught. Right. Again, let's verify this solution. So B prime C, that corresponds to the positions. Now we were trying to build a POS. So we're looking for zeros. And B prime plus C corresponds to the position in the Karnaugh map when B equals 1 and C equals 0. Again, when we deal with sum terms, the way we interpret the position is the opposite as how we handle products and min terms. Right? B equals 1, C equals 0. B equals 1 is the middle two columns. C equals 0 is the top row. So their intersection is this region. Right? That's when you have B equals 1 and C equals 0. Therefore, if those are a group of zeros, you describe it as B prime plus C. Right? So we got one of them. And that is indeed a pretty big sum term. You can now grow it further. Let's see the second one. The second one is A prime C prime. That is when A equals 1, C equals 0. A equals 1, C equals, plus C prime. So A equals 1, C equals 1. That corresponds to these two zeros. Right. And finally, B equals 0, C equals 1. That corresponds to these two zeros. Again, the edge wrap around adjacency. Right. And this is indeed a minimal POS. Very good job. Anyone got a different answer? Yeah. Top to bottom. Say that again. 110 and 111. They can also be grouped together, right? That's a true statement. These two zeros are adjacent, and then they can be grouped into a sum term. The question is, what is the minimal way to cover all the zeros? Right? You're trying to build a POS, you're trying to cover all the zeros. Without this yellow term, all the zeros get covered. Right? So these three, not refreshing. So these three sum terms, they cover all the zeros. So that is a correct expression. But there's another sum term over here that goes vertically. And that is also something that, it's not a subset of the other ones. But you can think of this yellow one as the consensus between this term and this term. Right? When we write it out as a Boolean expression, the yellow one will appear to be A prime plus B prime. That is the consensus between these two terms. C and C prime, those are the anchor points. You can combine A prime and B prime and create an additional term. And since it's consensus, you do not need to keep it in the expression. And that is what we need to do to get the minimum expression. But that's not the only answer. You could also keep A prime plus B prime, but then throw away the term of these two zeros. Right? Again, now you have an alternative solution which uses three sum terms to cover all the zeros. Right, in this expression, we're essentially throwing away A prime plus C prime. We're throwing away this one. And that is also a valid way of applying consensus. This is a consensus between these two, B and B prime. So A prime, C prime can be combined using the OR function to create a consensus term, which is redundant. Right, so really, you have four large sum terms, and you only need three of them. You can apply consensus by getting rid of this, or applying consensus and then get rid of this. Right? These are some of your choices. And both of them have the same number of terms, the same number of literals, and they have the same minimality level. And indeed, both of them are minimal expressions. Any questions about this example? Right, this just shows you that even though we're able to identify adjacency, we still need to search a little bit for the minimal expression. Right? It's not by just including all the ways you can group together min terms and max terms. It is also a way of selecting the best set of large products and larger sums to cover all the ones in the minimal way. Yes. Why do I circle this? For the sum of products, I'm looking for zeros. Sum of products is a generalization of sum of max terms. So I'm targeting zeros. My goal is to group together zeros to build larger sums, which means a sum with fewer literals, so that eventually I can use these groups to cover all the zeros. Oh, the other one. This is a min term, and the min term needs to be included in a sum of products or sum of min term expression. And when building an SOP representation, I need to cover all the ones. to include all the conditions that produce a 1 in my sum expression, so that whenever either of them produce a 1, the final output is a 1. So I need to cover all the 1s. Some of them have to be covered individually because it doesn't have any neighboring 1s. Some of them can be grouped together to become a larger product, which means a product with fewer literals. And then you just do the best you can to get a minimum expression. Right. So moving on, I just show you how to represent minterms and maxterms and products and sums in a Karnaugh map. You can, in fact, also plot XOR functions in a Karnaugh map. XOR function typically result in these kind of alternating zeros and one patterns. And I'll just highlight a few zeros and ones in each Karnaugh map. So this is the XOR between A, B, C, which means the output is 1 when you have an odd number of 1s at the inputs. 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1. Those are the 4 conditions with a single 1 or 3 1s, an odd number of 1s. So they should produce an output of 1. Right? And 1 happens in this alternating pattern. And this also makes sense in terms of Hamming adjacency. When you go from one cell to another cell, they differ by 1 bit. So you change from odd to even. And we'll flip again in either direction. You go from even to odd. So these odd number of 1 cells will never sit next to each other, just because neighboring cells differ by a single bit. They have a Hamming distance of 1. Right? And then secondly, you can also plot the XOR between 2 variables, A, B, A XOR B. So that will be 1 when A is 1, B is 0, represented by this group, or A is 0, B is 1, represented by this group of minterms. So really, the way I do plotting is I can convert this into an SOP, A prime B plus A B prime, and then put that in my Karnaugh map. Yeah, I don't really need a 3-variable Karnaugh map, since that's a 2-variable function. But you could put that in a larger Karnaugh map, and then C is of no use in this scenario. Right? The output does not depend on C. XNOR is the opposite of XOR, and this can be expanded into an SOP of AC plus A prime C prime. Right, so A is 1, C is 1, A is 0, C is 0. Again, I just circle out all the product terms, and then that is also the XNOR representation. Right, XNOR, they all have this kind of alternating 0 and 1 pattern. All right, what about a more complex function that involves products and XOR? In this scenario, visualization is a little bit more difficult. But we have we have seen one method of visualizing these functions in a truth table. If you want to see that in a truth table, what you can do is you can put down 1 column for A and B, 1 column for C, and then do an XOR between those 2 columns. We can do the very same thing with a Karnaugh map. In fact, Karnaugh map is no other than a different ordering of the truth table. Right? The information contents, these are your inputs, these are your outputs. It's exactly the same as the truth table, just ordered in a different way. And therefore, just like you can do some operation between 2 columns of a truth table, you can do some operation between 2 Karnaugh maps by effectively examining every position in each Karnaugh map and then put the result in the resulting Karnaugh map. So if we were to run the XOR between AB is 1 when A is 1, B is 1, XOR with C, the middle 2 rows, we can examine them cell by cell. So the first cell is 0, XOR 0, which gives you a 0. Second one would be 0, XOR 0, which gives you a 0. Right. Third one would be, let's say, 0, XOR 1, gives you a 1. And then you can just keep going. 0 XOR 1 gives you a 1. Right? Eventually, you get to fill out the entire resulting Karnaugh map. Right? So 2-level SOP POS, you can directly just plot the minterms and product terms in the Karnaugh map. For a more complex functional composition, you probably have to draw out individual Karnaugh maps and then compose them into the resulting Karnaugh map through the operation. Right. What we just did is essentially the Karnaugh map way of doing functional composition in truth table. 2 columns gives you a new column by running through a lot of zeros and ones through the composition operator. In Karnaugh map, 2 sub-expressions through some operation gives you the resulting composed function. Right, in this example, I have another expression, A XOR B and A XOR C. So I just have to put down in the Karnaugh map for A XOR B. So that's 1, A is 1, B is 0, or A is 0, B is 1. That's a sub-expression, a part of my main expression. A XOR C would be A is 1, C equals 0, A is 0, C equals 1. And then I want to compute the AND function between those 2 Karnaugh maps. Right, I can do it one by one entry at a time. I can also do a bit of grouping and then find out some of the kind of similar entries. So let's say this is when both K maps produce a 0. This is also when both K maps produce a 0. So with that observation, I can directly put down a 0 and 0 in the resulting Karnaugh map. I'm trying to find out the positions that have the same behavior so that I only have to run through them once. Or even better, since this is an AND operation, whenever either of the function produces 0, I know my output will be a 0. 0 and anything is 0. It doesn't matter where that 0 comes from, in either this function or that function. So whenever I see a 0 in either of the Karnaugh maps, I'll put down a 0 at the output function. Does it make sense? Essentially, I'm running it, this one with this one through the AND operator. 0 and 1 gives me a 0. But because I know the way AND function works is if you have a single 0 at the inputs, output will be 0. I just check for all the positions with a 0 in either of the 2 input Karnaugh maps, and then put down a 0 at the output. Or conversely, AND function produces a 1 only when both of the input functions are 1s. Right, so this is when both inputs are 1s. This is when both inputs are 1s. So I know those will be my only 2 1s in the resulting function. And if you compare this with the truth table, in the truth table, output is 1 when input is 0, 1, 1, 1, 0, 0. In the Karnaugh map, output is 1 when input is 0, 1, 1, and 1, 0, 0. So they really represent the very same function. Right. Any questions? All right. If not, we're going to move on to a larger Karnaugh map. Most of the Karnaugh maps we have seen so far are 3-variable Karnaugh maps, 2-variable or 3-variable. So 2-variable, the size is 2 by 2. 3-variable, the size is 2 by 4 or 4 by 2. 4-variable, you need 16 different cells, and that is a 4 by 4 Karnaugh map. Rows are ordered in that hemi-adjacent order, 0001, 1110. Columns are also ordered in the same hemi-adjacency sequence. Right. And pretty much everything you did for a 3-variable Karnaugh map will work exactly the same in a 4-variable Karnaugh map. Just a little bit more complicated, a larger function, more zeros, more ones. So it takes more resource, mental resource, to calculate most of the things. Minimum expression, do some plotting, the XOR, etc. Right? But fundamentally, it's the very same idea. So let's say if I want to map that function, the first example, ACD plus A prime B plus D prime into the K map. Again, this is sum of products, so I know each term corresponds to a group of ones. And then I just need to locate when A equals 1, C equals 1, and D equals 1. So A equals 1, C equals 1, D equals 1, that corresponds to these 2 cells. And then I can put down 1s in the Karnaugh map. All right, this is the first product term, ACD. And secondly, A prime B. That's easier to see. AB sits on one side of the table. So A prime B is A equals 0, B equals 1. So I can put down a row of 1s over here. And this is A prime B. And then finally, D prime. D prime is a very large group of ones. D prime is this row and this row. They both have D equals 0, so D prime covers both of those rows, which means I'll use a different color. The bottom and the top using the wraparound adjacency. Top row and bottom row, they are perfect neighbors to each other. So you can also group together ones like this. Right? And as you can see, there's a bit of non-optimality. This one is not the most optimal. You could have used a larger group of ones by growing it into the bottom, right, to essentially replace ACD with AC. And this is what you would do with the Boolean algebraic equation, right? D plus ACD. By applying elimination, we can get rid of the variable D. Right? Again, the same minimization can be observed from the K-map and also the Boolean expression. Right? So second example, again, the conversion between truth table, K-map, and minterm expansion and Boolean expression. You can do four-way conversion between these four representational schemes. Now we're giving you a list of minterms. Right? The question is, how do we map those decimal indices into the Karnaugh map? The first thing to check is the order. The axis definition, where is xy, where is yz? Right? Sometimes wx goes on the top, yz goes to the bottom. Sometimes wx goes here and yz goes to the top. You have to be careful about it. Like we're not intentionally trying to screw up. It's just sometimes examples and questions, they come in different flavors. Even in a working environment, people use all kinds of conventions. So really, you should be able to do this analysis regardless of the order of the variable definitions, right? The axis orders. So wx goes to the left and yz goes to the top. So you should read all the cells in the wxyz order. That's how the function is defined. F wxyz is telling you that you should follow the wxyz order. So this is really my index 0, index 1, index 2, index 3. 0000, 0001, 0011, that's 3, 0010, that's 2. And then keep going, 4, 5, 6, 7. And then 8 would be 1000, that is at the bottom. 8, 9, 10, 11, 12, 13, 14, 15. That's how we identify the decimal representation for each cell in the Karnaugh map. All right. Now it's only a matter of mapping those indices to 1 because I give you a minterm expansion, right? A summation of lowercase m, that's a minterm expansion. So I put down a 0, a 1 at position 0, position 2, 3, 5, 6, 7, 8, 10, 11, 14, 15. A lot of ones. Right? At this point, you don't have to worry about the decimal indices anymore. Right? Just focus on the ones. And then if you want to minimize it, the question is how to group together a lot of ones. And that would be this very big block of ones, which would translate into y, a single literal. And then you have two adjacent ones over here. That is w prime x z. And then what about these two ones? How do you group them? Any ideas how we deal with these two ones? Again, the goal is to cover all the ones to get a sum of product expression. And now I've covered all the ones over there except for these two ones. What do I do? Yeah, Qingyu? The top and bottom. Yeah, that's a good try. Any other ideas? The other side, top and bottom as well. These four, the four ones sitting at the four corners, those are actually neighbors to each other. Right? So remember for this, 2 by 4 3-variable Karnaugh map, right? This is when you flatten it out, but you also have neighbors on the left edge and right edge, right? So you have to sort of think of this as a cylinder to wrap it around. For 4-variable Karnaugh map, you grow 2 additional dimensions, right? So 4 by 4. So you first fold it like this into a longer tube, and to create adjacency between top and bottom of the tube, right? So maybe think of it like this, right? Like 4 variables wrap around on the edge, and then now you have 4 variables, top to bottom, and top and bottom are neighbors to each other. You have to sort of bend it, right, to assume them to be neighbors as well. So in this planar space, 2D representation, the 4 corners, they're actually neighbors, right? You fold it, these 2 sides are neighbors, you fold it, top and bottom are neighbors. So the 4 corners are also neighbors to each other. And that would be represented as the left and right, that is when z equals 0, so z prime. First and last row, that is when x equals 0, so x prime. That's how we describe the 4 corners. So in addition to edge wraparound, you also have corner wraparound for a 4D, 4-variable Karnaugh map. Right. And this is what I was trying to describe a minute earlier. With 2D, there's edge wraparound. And then with 4D, you sort of have, if you really want in a 3-dimensional space, it will be represented as a donut. And everything has 4 neighbors, like 1 to the left, 1 to the right, 1 to the top, 1 to the bottom. And this particular shape allows you for edge wraparound, and also top and bottom wraparound by going through this way into the donut and then out of the donut. Right? And as you can see, we would prefer that 4 by 4 table much more than this kind of weird shape. It's very hard to do any kind of minimization and then visually see anything from this. It's just too complicated when you put it down on a piece of paper. Right? That's the reason why we have the 2D 4 by 4, 2 by 4 tables. All right. And here's just some examples, ways that you can group together ones in a 4 by 4 4-variable Karnaugh map. Adjacent ones, group of 4 ones, right? Top and bottom, side and side, the 2 corners, a single row. Again, anything of the size of 2 to the n times 2 to the n, 2 ones, 4 ones, 8 ones, sitting in this rectangular shape that can be grouped into a larger product. Any questions? Yeah. Yes. Um, 2 by n times 2 by n includes 2 to the 0 times 2 to the 0, so including a single min term. Right? If, let's say, you have one over here, right? This is a valid way, a valid product term. Right? It's not the biggest. You can group it into a larger one, right, by going in the other direction. Right? But just keeping this as a singular term, that is also a valid product, just not minimal. Right? And if this one doesn't have any neighbors of ones, then you have to include it as an individual min term, a product involving all of the input variables. Right? Yeah, any other questions? All right. And then in the workbook from yesterday, we have a question similar to this. We give you a bunch of products, random through an XOR function. And then some people are asking me, do I do it using Boolean algebra? The answer is no. Just in general, you have to trust that all of the questions in the workbook and exam can be solved without a brute force method. If you want to do that in Boolean algebra, it's going to be super complicated. Just too many inversions. One term becomes multiple terms, 2 terms becomes 4 terms when you apply the XOR formula, and then you just get a lot of terms, a lot of busy work, and that's not what we're trying to do. And we want you to approach these questions from the Karnaugh map with this visual aid. And again, now I have an XOR expression of 3 terms. What I can do is I can first represent each term in the Karnaugh map and see how they overlap and how they interact. For example, if for this example, A prime, C prime, that corresponds to this cube. A equals 0, C equals 0. BD is the middle one. AC is this bottom right. Right, those are the positions, the shape of 3 of the products. And now if I run them through XOR, what's going to happen? Any ideas? I want to run them through an XOR. I could have put them in 3 separate Karnaugh maps and then put this as my 4th Karnaugh map for the resulting function. But just for convenience, I can just circle the position of these implicants and then conceptually think about the question, what's going to happen if my input value sits over here in terms of its impact on the 3 products. Right. Maybe I should give you a more concrete task. What do you think will happen over here? Yeah, Eric. Very nice. We would have a 0 over there. Right? And the reason is covered by 2 product terms. So it will produce an output of 1 in 2 of the terms going into the XOR function. And the last one, when it's not covered by that product, it will produce a 0. And 1 XOR 0, you have an even number of 1s, which gives you an output of 0. And we can verify that algebraically. Right? So the input at that point is 0, 1, 0, 1. 0, 1, 0, 1 on A, B, C, D. So 0 prime times 0 prime is a 1. BD is a 1. AC 0.0 is a 0. So indeed, you should get an output of 0. We can see that much more easily through Karnaugh map. When this is covered by 2 products, it will produce 1 at these 2 terms and a 0 at this term. So 1, 1, 0 gives you a 0. And by the same analysis, this one would also be 0. It's covered by 2 products. So resulting in 0 in those 2 terms on the right. And the first term will produce a 0. So 1, 0, XOR 1 gives you a 0. When something is only covered by 1 product, it will only produce a 1 for that single product. So 1 XOR 0 will give you a 1 in all these remaining cells. What about those outside places? Yes. They're all zeros. When they're not covered, they'll produce 0 in each and every term. Right? So it's all zeros. Right? Now we just plotted that complicated function into a Karnaugh map by analyzing the relationship of these product terms, whether they overlap or not. And again, don't remember this as a rule. Right? We expect you to be able to analyze them. Sometimes you see with a small tweak, the whole picture will change. If I replace those with, let's say, XNOR, right? I replace the term with some sums. Like this entire analysis will be, the analysis will be different. Right? So don't memorize it, but try to approach it from this conceptual picture, how they overlap. What does this mean for each term? And then run them through the top level function, XOR in this case. So to sum it up, we can use Karnaugh maps for many things. We can use it to represent functions, to show a list of min terms, max terms in this 2-dimensional representation to better visualize adjacency. We can use K-map for comparing functions, for example, right? Give you 2 different Boolean expressions. In that consensus example, 2 different set of product terms. You can compare them by plotting them into 2 separate K-maps and see if these 2 K-maps are the same. You can use it for logic minimization, finding out the best way to group together zeros and ones to get a product sum or sum of products, respectively. You can use it to evaluate more complicated functions by visually locating each term within the K-map and then see how they interact. Right? And again, all of this is operating under the same framework of Boolean algebra. So anything that you can algebraically do can also be done with the help of Karnaugh maps. But you see, with Boolean algebra, you can write down 10 variables, 20 variables. It gets more complicated, but you can still do it. But with K-map, 4x4 K-map only supports 4 variables. And it's actually very difficult to go above 4 variables. We tried to do a 4x8 or 2x8 K-maps over here yesterday. If that works, that would support 5 variables, but it does not work. Like this adjacency, some of the relationship gets lost when you go beyond 4x4 4-variable K-maps. All right. There's still a missing piece, which is don't cares. Remember, we talked about don't cares in a truth table. The output could be 0, could be 1, could also be an X, meaning that that input condition will never happen, so I don't care what the circuit produces over there. And we can also put don't cares in a K-map. This function, again, now the first thing I do is I'm going to verify the order of the inputs, A, B, C, D. And now AB goes to the top, CD goes to the side. So my index will go from 0 to 1 towards the bottom first, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? It used to be, in that previous example, we counted this 0, 1, 2, 3, but now we're counting 0, 1, 2, 3 because the axis definition changed. And again, I can put those min terms in the Karnaugh map by following position 1, 2, 3, 5, 7, and 9. I can also put down the don't care terms at the corresponding indices. So 6 is a don't care, 12 is a don't care, 13 is a don't care. Right, I'm just following the indices, but if it's a min term, I put down 1. If it's a D, denoted by that lowercase d, I put down an x. Right. At this point, if I were to minimize the function, I can just erase all these indices. It makes my life a little bit easier because I can just concentrate on the zeros and ones and don't cares. Let's say if this is the function, the minimum sum of products ways to group together ones. You can make use of the don't cares if you like, right? If they help you grow a larger products. But if they're of no use, if they're a little bit distant from your groups of ones, you can also treat them as zeros. Right? You can treat them to whatever you like. The one that gives you the most logical minimization would be preferred. So how would we do that? Well, I think I'm going to do this one, and this one, with only 2 products. Each of them is pretty big, right, to cover all the ones. And these don't cares will be treated as ones. That don't care will be treated as a 0. And if I were to write it out, the function becomes C prime D plus A prime C. And this is indeed a minimal sum of product expression for the function. All right. It's not that complicated, right? So don't care is just a way to additional notation that you can put in the table, and you can make use of them to create bigger products if you like, if you find them to be useful. And that one that sits very far away from the other ones. So just treat it as a 0, and you don't have to worry about covering it. All right. So what have we been doing so far? We defined multiple things. We defined product terms. We defined sum terms. And the way we do logical minimization, we haven't really got an algorithm yet. Visually, you're trying to group together ones and then finding the best way to cover all the ones. But what defines the best? Right? Like in general, how do you find the best? That is a question that we have not addressed. We're going to address that right now. To develop a formal algorithm, I need to introduce a few more definitions. Number one is prime implicance. I think I misspoke implicance a few times before because once you learn something, it's very hard to unlearn. But implicant is really just a product. A product equals an implicant. I think the reason is because implicant means something that gets implied. You have all those ones. These conditions combined will imply a larger term. So a product term, starting from this point, will be called an implicant. A prime implicant is just a product term that cannot be grown any further, the largest possible implicant. If you look at this table, right, I'm circling out some of these individual terms or even some of the groups of ones. And this is a product, all of them are products. A min-term product, a product with one fewer variable. But all of them are not prime. I mean, they're of inferior quality because these two can be combined. In other words, this product can be grown into a bigger product. This product can be grown into a bigger product. And to get a minimum expression, I only need the biggest products. The biggest products have fewer literals, and therefore they're of higher quality. In that K-map, now I'm illustrating all the prime implicants, the one that cannot be grown any further. This one is already maximally expanded. You cannot grow it to the top. You cannot grow it to the right because those are all zeros. You cannot grow it to the bottom because this is a 0. So this has already been grown in all the possible directions. And therefore, it's a prime. And this top and bottom, again, they cannot grow to the right because this is a 0. They cannot grow to the top because these two are zeros. They cannot grow to the other side because this is a 0. So again, this top and bottom wraparound implicant is also maximally grown. And these are the largest possible implicants, and these are the only things that we'll use for a minimal expression. Right. So another example. Right. Now, a new K-map, you can find prime implicants by just grouping together all the ones so that they cannot be grown any further. Right. So these are all the prime implicants, including these 4 ones at the center. None of them is a subset of another implicant. This is the largest implicant possible. And in this example, the minimal expression would involve 4 implicants, right? Anything but the middle one. The middle one, even though it appears to be very large, it is not needed. It doesn't provide any additional coverage. These implicants are something that I definitely need to include because those are the only ones that cover this min-term, this min-term, this min-term, and that min-term. Right? I have no other choices but to pick those 2 min-term prime implicants. Once I include those essential ones, the middle ones is no longer needed. I already covered all the ones. Right. So the idea is we don't need to include all the prime implicants. Prime implicants are the only possible candidates, but we still need to make a selection within prime implicants. Right. So to better appreciate the benefits of prime implicants, I'm presenting the same function over here with 2 different sets of implicants. And let's assume that we implement our circuit using this set of implicants or that set of implicants. Each of them will result in a sum of product expression. Right? I want you to count the number of gates in the resulting circuit. Right? I'll give you 2 minutes to work on this exercise. Right? Count the number of gates by sort of think of these implicants as a circuitry, a product implemented by an AND gate, and finally implemented with an OR gate in a 2-level sum of products. And then see how many gates we have and how many gate inputs do we have. If anyone needs some help, just let me know. We have another 25 seconds. Mark, did you get the counting? Yeah, you get the expression for it, right? And then that expression will translate into a particular gate structure, right? This is an AND gate, a single AND gate. 3 variable is a 3 input AND gate. And finally, you have to use a single OR gate to collect everything together, right? So we're asking to, for one thing, find out the expression, but also count the number of gates and how many inputs do we have in total. Right. Michael, did you get it? The first one?
4
Very nice. All right, time is up. So here's the answer. This one is an individual mean term, and it's going to be implemented using 4 variables, which translates into a 4-input AND gate. An AND gate with 4 input variables. This one, 3 variables, so 3-input AND gate. Those two are also 3 variable expressions, right? 3 variable implicants. So they translate into a 3 variable AND gates. And then finally, you have 4 terms in total, and they need to be collected by a single OR gate to produce the final SOP function. So if we're to draw the circuit, it will look something like this. OR gate at the bottom, 4 AND gates at the front, one of them with 4 inputs, and the other 3 all have 3 inputs. So 5 gates in total. And how many gate inputs? It's going to be 8 plus 9, so 17 gate inputs. 4 plus 3 plus 3 plus 3 plus 4. That's what I'm counting. For each gate, the number of inputs, take the summation of all of them. The other implementation, now I have 3 terms, so I need a 3-input OR gate at the end. And now this 4 midterm term, that is A, C prime, so 2 literals, that is a 2-input AND gate. And then the other one, 2 midterm implicants gets translated into 3-input AND gates. So again, I have 3 AND gates, one of them with 2 inputs, the other 2 with 3 inputs. Right now I have 4 gates. And 2, 3, 3, 3, 11 gate inputs. A considerably smaller circuit compared to the first implementation. And this is what you get by only using prime implicants. To be able to cover ones using as few implicants as possible, which translates into fewest gates in the first level. And also, because they are prime, they cannot be grown any further. That is the one with the fewest gate inputs possible. So again, minimality is defined as minimum number of gates and minimum number of gate inputs. In other words, in a 2-level SOP representations, that means the fewest products, and then secondarily, the fewest literals going to the products, which means every product needs to be as big as possible. By growing the products, you can get rid of 1 additional variable. So prime implicants have the fewest variables. And therefore, the minimal expressions must contain only prime implicants. And you can also approach this proof from the opposite perspective. If you ever included a non-prime implicant, you could have replaced it with another prime implicant to realize the same function, but with fewer literals. And that's the reason why we only care about prime implicants in minimal implementation. Right. So moving on to the next example, I think we have done a lot of exercises. So I'll just do this together with you guys. Finding the prime implicants. All right, this is a prime implicant. I like to go from the largest implicants and then move on to smaller ones. All right, this is a prime. This is also a prime. This one is also a prime, the vertical one. Right. And this one is a prime. This one is also a prime. Okay, I'll use some different colors. A prime implicant, a prime implicant. Right. Did I miss anything? think I do. Yeah, the wraparound. Right, this one is also a prime implicant. Right. The process of finding prime implicants does not depend on the minimal cover. Right, that is really a second question. We first need to find out the prime implicants and use them as candidates. And then at the second step, we'll select the best use of these implicants to cover all the ones. Right, these are two separate problems. All right. So given this set of implicants, the next question is how do we do the selection? Right? Again, now we are defining the logic minimization problem as two steps. Step one, finding the candidates, which are my prime implicants. Step number two, picking the best of these implicants to cover the ones using as few of them as possible. And secondarily, if you have a choice between large implicant and the smaller implicant, pick the larger one. And based on this set of implicants, you see, there are some minterms that are only covered by one prime implicant. This one is only covered by a single prime implicant. This one is covered by two. This one is covered by two. This one is covered by two. And when you see this kind of behavior, a minterm is only covered by one prime implicant, that prime implicant is said to be essential. There's no other prime cover without this prime implicant that uniquely covers a minterm. You have no other choices. Minimum cover requires prime implicants, and you must use that prime implicants to cover the minterm, which means in your final expression, you must include this prime implicant. And that is the definition of essentiality. Right. Again, all the implicants are shown over here. If there's a minterm that is covered by only one prime implicant, that prime implicant is said to be essential, which means you must include that in the minimal SOP expression. And similarly, in the same AND or two-level circuit. So in this function, we really have two prime implicants that are essential. This one is essential because of the one sitting at the top left. It's only covered by one implicant. So this implicant will be included. This one is essential for the bottom right minterm over there, only covered by one implicant. So I have to include that in my expression. So functionally, I'm doing this. I'm representing the final function as a sum of products by including BC prime plus AC. I have no other choices. And now I can use this as my starting point and then try to cover the remaining minterms. Right? There are only these two minterms that have not been covered. And you have many choices of covering them. But the best way is probably using a single term to cover both minterms. Right? And that is the vertical implicants over here, which is not essential. But once you have included all the essential ones, this is the best way to cover the rest. So I'll put that in my final expression, A prime, B prime, D. All right. Any questions so far? All right. Then I just have more examples. Okay, let's do this together. The first task is to find prime implicants over there. I like to start from the largest. So I want to look for groups of 8 ones. There's none. And then group of 4 ones. Then this is a very large implicant. And that's the only group of 4 ones. And then I'll probably move down to groups of 2 ones. Right, so this is a prime implicant. This is a prime. This is a prime. This one, remember the wraparound top and bottom is also a prime. And once I've found all the prime implicants, you need to check their coverage to see if there's any minterm that is only covered by one implicant. Right? I'm seeing, well, these two minterms, they're only covered by one implicant. Right? I mean one prime implicant. This one is only covered by one. This one is only covered by one. So the corresponding implicants must be included in the minimal expression, which means this is my first implicant to be used for the final expression. This is the second one. It uniquely covers a minterm. And then this is my third. And once you have done that, you have to essentially try out the remaining possibilities. But you're only left with a single one to be covered. And that one can be covered by either this one or this one, right? One of them. This is a systematic algorithm, right? You're not just searching from the original K-map. You're first doing some pruning, getting most of this essential information out of the way to make the most use of it to simplify the problem. And after simplification, the problem typically becomes much easier to solve. At that point, you probably just have to try out the remaining possibilities. And there are usually not many possibilities left. So to summarize the K-map simplification steps, step number one is to identify all the prime implicants. And we identify them only for the sake of finding essential prime implicants. And then once we find essential prime implicants, we need to include them in the expression, and then come back to examine the K-map to see which minterms have not been covered, and then try to optimally cover them. And remember this principle of duality. We have zeros, you have one theorem, you have the opposite side of the theorem. And if you have implicants for minterms, you also have implicates for maxterms. So implicates are essentially sum terms, right? Or a function of several variables. It's called implicates, and I don't know why it's called an implicate. Any ideas? Well, I guess someone just found it to be a cute name and then arbitrarily assigned calling them implicates. But it's just something I have to remember. Implicants makes more sense. Implicants for minterms and products. Implicates for maxterms, zeros, and sums. Prime implicates and implicates that cannot be grown any further. Right? What I did over here is I'm just replacing all the ones with zeros. So now this is a new function. And the way you find prime implicates and essential prime implicates are really the same method as finding prime implicants and essential prime implicants. Right? Just now you're looking at zeros instead. That's the only difference. Again, this is one implicate, one sum term, one implicate, one implicate, 1, 1, and 1. Right? Same shape as before because I'm only replacing zeros and ones with zeros. And the essential ones will be this max term is only covered by one implicate. So the implicate is essential. This max term is only covered by one. So the corresponding implicate is essential. And if you want to find a minimal POS expression, we need to include this essential prime implicates, and then represent the remaining zeros using some other prime implicates that are not essential. So just to complete this example, I will write out the expression for this function in a product of sum fashion. So function is equal to, start with the top middle implicates. That is when b equals 1, c equals 0. So as a sum term, I write it out as b prime plus c. And then I need to multiply it or AND it with a prime plus c prime, and then AND it with a plus b plus d prime. Right? Implicates equals sums. So the way we find max terms, we find sum terms from K-map will be the same for implicates. All right, again, if I want to draw this as a circuit, I would have an AND gate at the output and 3 OR gates at the front. Right, this one has 2 inputs, and 3 inputs. And you just connect the corresponding variables, sometimes with an additional inverter, to the circuit inputs, and that will be the final function. All right. Any questions? So this is the last topic I want to cover, about finding prime implicants and implicates and essential ones with don't cares. Actually, the definition of prime and essential prime remains the same. This is a new function with don't cares. And our goal is to find prime implicants. Prime implicants are the ones that cannot be grown any further. And in finding prime implicant, you essentially have to treat all the x's as ones. Just view them as ones to find the largest group of ones. Right? This is one prime implicant. This is another prime implicant. We just treat all the don't cares as ones. When it comes to essentiality checking, we only care about the true minterms of the function because the don't cares don't have to be covered. And even though, let's say, this implicant is the only one to cover the don't care, because the don't care does not have to be covered, the implicant is not necessarily needed. Right? So when checking for essentiality, we only care about the true minterms. And this minterm is covered by two implicants, and that's the only minterm. So we do not have any essential prime implicants. We have two implicants, but none of them is essential. Right? The same analysis goes for implicates. Again, when we look for implicates, we check for zeros and x's. We assume x to be zeros so that I can maximally grow my implicates. But when it comes to essentiality checking, I only check for zeros. And in this case, this is a different function. You have a single zero covered by only one prime implicate. So that prime implicate is essential for this zero. And this part is also essential for the zero over here. And I want you to try out this exercise. Right, for this function, try to find out how many essential prime implicants we have, and then finally build a minimal SOP expression. I'll give you 2 minutes to work on this exercise. Right. One hint I want to give you is that to find the essential prime implicants, technically, you need to first find all the prime implicants. But that is not really necessary. Sometimes you can directly eyeball something to be essential by observing the neighbors of minterms and see if those directions are blocked, these directions are open, I can probably only go this way, and then that's the only choice to cover a minterm. So it's up to you whether you want to find all the prime implicants or you want to directly go to essential prime implicants. Another 1 minute. All right, time is up. Melissa, did you find any essential prime implicants? Maybe give me one if you find any. Or you can just show me where it is and then I'll point it out. The one at the top left corner. All right. To prove that something is not an essential, you have to essentially prove that both of the minterms covered by the implicant can also be covered by some other prime implicants. Right? And then I can show you 2 other prime implicants. Like this is a prime implicant. Right? This is the 4 corners. It's another prime implicant. And therefore, those 2 ones are not essential. There are additional prime implicants that can be used to cover those 2 minterms. Hamza, did you find any prime implicants?
Just like here.
And then you want to have this group of 4. Yeah, this group of 4.
So I think
Yeah, Hamza is saying that this is the midterm that makes that implicant essential. And that is true. If you look at that midterm, it can only be covered by this prime implicant. Yeah. So this is indeed a prime implicant. And then I'll just do the rest. This is also a prime implicant because of this midterm. Right? See, the way I find prime implicants is by looking for its neighbors. It has 2 zeros. So 0 kind of like block the growth of the midterm in those directions. And it has already fully grown in this and these directions. And there are only 4 directions in total for 4 variable K-maps. So this must be essential. Any other essential midterms? Sorry, essential prime implicants? Anyone found some others? All right, in fact, these are the only essential prime implicants. And again, to cover a function, we need to include all the essential prime implicants and then trying to find the best way to cover the rest. And I would say, well, to cover this one, I can use this 4 midterm. To cover the one on the right, I need to use these 4 midterms. And that would be a minimal cover. First, including the essential ones, including them in the final expression, and to simplify the problem, and now you're only left with 2 ones to cover, and they can now be covered by a shared implicant. So 2 additional implicants would be the best. Right. So to recap on what we're trying to learn over here, there are 2 things, the 2 main tasks that we're trying to accomplish in this class. Number 1 is implementation and optimization. That is a conversion between a behavior description into an implementation. The opposite one is analysis. Given a circuit, try to figure out what it does. Right? Given a Boolean expression, try to reconstruct the truth table and then see how it functions. We have seen that in our first example for a 1-bit half adder, the adder without carry-in, to go from the behavior description in terms of binary arithmetics all the way to the implementation. And over there, we use truth table as our intermediate tool. And now we have seen K-map. We can also use K-map over here, right, to make the implementation happen. We have also seen that for this autonomous driving vehicle, for this pre-acceleration module, where let's say 1,1 is never received as an input from that planning module. So this is a don't care condition. And then we can interpret it to, we can write out this expression also in terms of an equivalent minterm expansion and maximum expansion with don't care terms. And this, so far, this is still the specification. And to implement it, we have to assign a particular value to the don't care. Right? If it's a 0, we get an XOR implementation. If it's a 1, we get an OR implementation. And then once we get that implementation, we can write it out as a circuit. But once you do the implementation, you essentially assign some value to this don't care. Right? You assign this to be in that OR implementation of 1. So it's actually impossible to go from the implementation back to the specification because don't care has already been fully specified in the implementation. A Boolean circuit is always fully specified because you can send in any inputs, 0, 1, 1, 0, 1, 1, 0, 0, and then it will produce some output. So the implementation is always fully specified. Therefore, once you implement, it's very hard to go back. Right? From that OR function, you can now tell which of these 3 is a don't care, or even in this one, is it a don't care or not? You cannot really tell. Right? And this problem, implementation and analysis, is a problem for both software and hardware. For software, implementation is called compilation, the conversion between a human understandable code into some assembly code. In hardware, it's called synthesis, the conversion between some hardware description language, a behavior description, into a circuit implementation. And analysis and implementation, these are like equally important tasks. In other words, engineering, the implementation task, and reverse engineering, the analysis task. Both of them are very important engineering problems. And for both software and hardware, you need to be comfortable with both to be able to do things like debugging, analysis, optimization. You have to be able to go in both directions. So that's the reason why we are trying to go in both directions, to implement it, but also analyze it with the help of truth table, K-map, and expression. So that's everything for today. Yeah, that's it. And then any questions about the midterm, by the way? Right, it's coming on Tuesday. Any questions? Yes, Melissa.
Any
Huh? I don't know, but I would say around 12 questions, like 12 to 14. But it really depends on the complexity of the question. Right? It could be like more easier questions or like fewer harder questions. But I'll try to make it reasonable. Yeah. Yes, around that.
Does it go up to this?
Yes, until this lecture. Next Monday is a review. Yeah, and no new material. Even though there will be a workbook for Monday, it's not a real workbook. It's more like a survey. Right? Completing a survey, then get like 2%, 3% of the work points. And no workbook for Tuesday. Right. Yes. Yes, it will be held here during lecture. Yeah, no one wants to leave. Yeah. Yes. I will share you some questions. Yeah, I'll share you a document with some practice questions, and also I'll tell you the topic of the actual question on the exam in that document.
So kind of like a study guide.
Yes. Yeah. Yeah.
You said we get practice like by a midterm somewhere here.
Yeah, I'll share it in Slack.
Oh, okay.
Yeah, I'll share you a link to overleave.
Okay, I couldn't
Yeah.
find it here. Thank you.
Yeah, it's not there yet.
Is there going to be online for the midterm?
Online midterm?
That's similar to like
No, it's here.
Or outline? Like
Outline for the midterm. Well, what do you mean outline?
it's like what's being tested, what's not being tested. I don't know.
Oh, I'll tell you the exact topic of each question. That's more than an outline.
Oh, okay.
Yeah, I'll probably, for example, I'll tell you that there's a question about two's complement addition with 4-bit numbers, something of that sort. A
Okay.
pretty detailed description.
Okay.
Yeah.
represented here.